Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show a simple example of forced flow convective heat transfer through perforated plates using SolidWorks flow solution. Initially we'll perform one CFD analysis. Next to that we'll go for parametric study and optimization. This is our model. For understanding the model, let us cut this one from front plane. So at the bottom part we have provided one heat surface which will be providing heat at a rate of 1000 joules per second, and next to that we are providing some fins. Fins are made up of aluminium. At the side walls we have provided perforated sheets. The sheets are actually having circular profile perforations with a specific diameter, and you can see the top part, and this is known as walls, which is also made up of aluminium. And to provide air from the top at a high rate, we have provided one fan at this location, and this is the lid. Let us start our simulation. The flow simulation environment will be created with the wizard itself. Let us start from wizard. We are keeping the name of the project as the default project 4. Next to that, we are selecting the unit system as SI, and if we want we can go for some kind of user defined unit system also, but we are keeping the unit system as SI, and we want temperature to be in degrees Celsius. Let us change the angular velocity to be revolutions per minute or rotations per minute. Next, it is an internal analysis. Next to that, we have to consider heat conduction in solids, and definitely gravity will be involved as heated air will be moving upward, and the direction of gravity will be y. So along y direction it will be minus 9.81 meter per second square, and along z component its value will be 0. And rotation will be involved as from the top we are providing one fan for initiation of forced flow convective heat transfer. Next to that, we have to select that gas. We'll consider air as the gas. Next to that, default material we'll consider as aluminum alloys, that means aluminum 6061, and the other materials will be provided while applying boundary conditions. Next to that, the default outer wall thermal conditions and roughness we are considering. Atmospheric pressure will be 10135 Pascal and temperature will be 20 degrees centigrade. Solid parameters also it will be 20 degrees centigrade. Let us finish this. You see this is the computational domain. Now let us hide this domain. Next to that we have to provide our boundary conditions. We have already initiated rotating regions that will be provided with a specific rotations. Insert rotating regions, and we have to select the rotating regions from here. We have renamed that one as fan from the solid entities, and let us provide the rotation of that fan to be 10,000 rpm, and minus sign is provided to have a specific direction of rotation to be in the anti-clockwise direction. And we can check from the component control options that while considering this analysis, fan will be disabled. Next to that, we have to provide our heat source. We can provide a heat source for conditions, surface source. Let us select that heat source from the solid entities. It will provide heat at a rate of 1000 watt. Green check. Now we can apply boundary conditions. Insert boundary conditions. It will be environmental pressure at the top lid. Select other. It will be first lid number 1, and we are providing environmental pressure at the top lid. Green check. And while providing perforated sheets, again we have to provide that atmospheric pressure inside. We can provide boundary conditions at the perforated plates. Insert boundary conditions. It will be environmental pressure at the perforated plates. Select other. Let us select it first. Selected, it will be equal to environmental pressure. Again check. Next, from the conditions, we can provide perforated plates. Let us select that location from here, and we can provide predefined or user-defined perforation. Let us provide user-defined perforation with a specific diameter. New perforated plate, and let us see the properties of new perforated plate. We have already provided this one to be diameter as 0.202 meter, and free area ratio is equal to 0.4. Selected. Green check. Next, we have to select some goals. Insert goals. In this case, you have to select some global goals. You're going to have maximum, minimum, and average temperature of fluid. By the same time, that of solid also to be taken. So we are selecting minimum, average, and maximum temperature of fluid. By the same time, we'll take total temperature of solid also. Green check. You have selected 6 different global goals. Green check. Next to that, we can run it with the new calculations. The solver window has already started iterations. The solver is finished, and from here you can see that minimum temperature of fluid is minus 8.99 degrees centigrade, and that of maximum temperature is 51.66 degrees centigrade. And you can see our goals from here. You can see all the goals are converged. It is clearly visible that minimum temperature of solid equal to minus 13.484 degrees centigrade, and that of fluid is minus 8.99 degrees centigrade. And similarly, maximum temperature of fluid is 51.68 degrees centigrade, and maximum temperature of solid equal to also same, it is 51.68 degrees centigrade. And the average temperature of fluid is 21.89 degrees centigrade, and that of fluid is also 21.89 degrees centigrade. Now we'll see all these things from our cut plots. Let us close this. We'll see the results from cut plots. Results. Insert cut plots, and we want to see temperature of fluid from front plane. Green check. Let us see this cut plot as an animation. Cut plot 1. Let us play. You can see how heat is being generated at the middle position, and by forced flow of air from the top side, it is being cooled. The fins are being heated up by the heat source, and the color you can see at the middle position is red. It is indicating that temperature at the middle position is 51.68 degrees centigrade, and by the forced flow of air from the top side, it is being cooled. Let us see the temperature of solid also. So base side it is having heating source, so its temperature is in the range of 52.4 degrees centigrade indicated by red color, and top side you can see the temperature is very less, it is in the range of blue zone, that means 20 degrees centigrade. So solid is having temperature, minimum temperature is 20 degrees centigrade and maximum temperature is 52.4 degrees centigrade. Let us clear and hide. Next to that, we want to see surface plots. Insert surface plots. We want to see temperature of fluid at all surfaces. Green check. You can see here at different levels, you can see different ranges of temperatures. This is the temperature of fluid at different levels. At the ground level, the temperature is in the range of 20 degrees centigrade, indicated by green color. And next to that heat source, temperature ranges in the range of 45 to 50 degrees centigrade. And as it is going up, temperature is reducing. At the top surface wherefrom we are providing forced air, that temperature is in the range of 20 degrees centigrade. Okay, so let us clear and hide these things. Surface plot 1, clear and hide. Next to that, we want to see the most important part, that is our flow trajectories. That is how the air particles will be moving from top lid to the downward direction with a view to have forced flow air. So flow trajectories, insert flow trajectories. We're going to see that flow trajectories from top side, and instead of 20 numbers, we'll make this 100. And instead of pipes, we want to see the flow trajectories in the form of arrows only. And the size of particles, we want to be a little smaller. Instead of 0.02 meter, we want to make this one 0.007 meter. Let us select the lead location. Select other. Let us select face at lead number 1. Selected, green check. Now you can see the particle study here. Let us view the scenes from the front plane. Let us play this. Flow trajectories, let us play. You can see how the air particles being driven or forced out from the fan, and it is cooling that fins, and from the side walls of the perforated plates the air particles are moving out. So it is clearly visible that forced air by the fan is cooling these heated fins, and finally after cooling these things, the air particles are moving out from the perforated plates at the side walls. It is clearly understood that at the bottom part, the air particles are heated up. It is in the range of near about 34 to 42 degrees centigrade, indicated by yellow color. At this range, the temperature is in the range of 34.88 degrees centigrade. And as we are moving up, the temperature of forced air is decreasing. It is in the range of near about 12 degrees centigrade. Next to that, we will go for some kind of parametric study, and we will vary the fan speed. So let us clear and hide these things. Solve new parametric study, and from here to go for design of experiments and optimization. For that, you have to select that input variables. Let us select the input variable as the fan speed. It will be obtained from the boundary conditions. Let us select that rotating regions from here. Angular velocity of the fan is selected as the input variable. Green check. We have to specify the range. Initially it was 10,000 revolutions per minute. Now we will change the range from 9,000 to 5,000 revolutions per minute. Green check. It will select that output parameters and it is dependent on goals. You can select all the goals, but our main aim is to see the maximum temperature of fluid and minimum temperature of fluid, right? You can select minimum temperature of fluid and maximum temperature of fluid as the main goals. Check. Let us see the scenario. Let us create 5 numbers of experiments. We have defined already with the different input variables. Let us make the angular velocity with this proper sequence. We are starting from minus 5,000. Let us make the first one as 5,000 RPM. Second experiment will be 6,000 RPM. Third one will be 7,000 RPM. Fourth one 8,000 RPM, and the final one is 9,000 RPM. Minus sign is indicating the direction. It will be in the anti-clockwise direction. So with these different input variables, let us create our parametric study. Let us run our parametric study with this input variable from 5,000 RPM to 9,000 RPM on the fan rotation. Let us run this. SolidWorks has already started iterations. It will take some time for getting all the results. Let the iterations move on. Whenever it is finished, we'll see the results and go for analysis. We can see all the results are converged. With defined input variables, we got our results that when the angular velocity of fan was 5,000 RPM, during that time we got our maximum temperature of fluid as 76.49 degrees centigrade and minimum temperature is 14.69 degrees centigrade. When the angular velocity of fan is increasing, in that case we are getting better cooling. That is visible in the experiment number 2 when the angular velocity was 6,000 RPM. That minimum temperature is 8.57 degrees centigrade and maximum temperature of fluid is 56.72 degrees centigrade. That means we are providing better cooling with higher angular velocity. Again, when the angular velocity of fan is 7,000 RPM, in that case we got minimum temperature of fluid is 5.19 degrees centigrade and maximum temperature of fluid as 66.99 degrees centigrade. Some kind of non-linear relation is there actually. Again, when the fan speed is 8,000 RPM, then minimum temperature of fluid is 1.09 degrees centigrade and maximum temperature of fluid is 64.93 degrees centigrade. And finally, when angular velocity of fan is 9,000 RPM, in that case minimum temperature of fluid is minus 4.46 degrees centigrade and maximum temperature of fluid is 48.67 degrees centigrade. And while checking this data, we have to remember that normal temperature or room temperature was 20 degrees centigrade. So from 20 degrees centigrade, we have provided better cooling with the higher fan speed, and the temperature of inside air also reduced from 20 degrees centigrade to minus 4 degrees centigrade, and heated surface temperature also reduced, and final temperature of heated surface is maximum temperature is 48.67 degrees centigrade. From this relation of parametric study, we got some kind of idea that when the fan speed is increasing, we are getting less temperature of air inside that one, right? We are having minimum temperature of air at 9,000 is minus 4 degrees centigrade and maximum temperature of fluid equal to 48 degrees centigrade when the RPM of the fan was 9,000. Now with this data we can go for some kind of optimization, that we want to have the minimum temperature of fluid to be certain amount, and for that what should be the RPM, right? Suppose we want to have the minimum temperature of fluid to be 10 degrees centigrade. For that what should be the RPM, that to be defined right now. So it is clear that for getting temperature to be 10 degrees centigrade, we have to keep the RPM in between 5000 to 6000, right? So in the next analysis, we will go for optimization, and in that case, we will finalize the angular velocity in the range of 5000 to 6000. Okay, so we can check. Next to that, we will go for optimization. It will come from here again, solve, new parametric study, and we have to go for goal optimization. And our task will be to have the minimum temperature of fluid to be 10 degrees centigrade. And for that, we have to depend on input variables. We are planning to take the input variable as angular velocity of the fan, and that should be specified in the range of 5000 to 6000 RPM. So let us select those input variables from here, and we have to consider that the input variable from rotating regions. Let us select the rotating region angular velocity as the input variable. Go and check. Now we have to define that range. It will be from 5000 to 6000 RPM. So we can define this range from minus 6000 RPM to minus 5000 RPM. Here minus sign indicates actually direction. It will be in the anti-clockwise direction. The angular velocity of fan is specified. Next to that, you have to select that goal. Let us see the output parameters, and it is dependent on goal. We have to select only one goal. We want to have the minimum temperature of fluid to be 10 degrees centigrade, right? So select the minimum temperature of fluid as the main goal. We'll check. Let us select the criteria, and we want to provide the target value to be 10 degrees centigrade. It is dependent on goal. Goal is minimum temperature of fluid. Now we have to provide the target value. The target value should be 10 degrees centigrade, and we want to achieve this target with a variation of plus minus 0.1 degrees centigrade. We'll check. Let us see the scenario. It is allowed to have maximum 128 numbers of iterations within the range of 6000 RPM to 5000 RPM. Let us run this one. Initially, it will start iterations with the maximum speed of 6000 RPM. Next case, it will start iterations with the minimum one. In this way, it will try to minimize the gap in between and finally optimize. Let the iterations move on. We can see our solution is converged. In fifth design point, we got our results with a discrepancy of 0.04. Our target value was 10, and when the angular velocity of fan is 5600.69, we got the minimum temperature of fluid to be 10.048 degrees centigrade. So this is our result. In this way, we got our optimum value at a specific angular velocity of 5600.69. We got the minimum temperature of fluid to be 10 degrees centigrade. Okay, this is all about our today's analysis. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.